In Year 11 chemistry, you're going to need to know about metallic bonding. As you can see here, the vast majority of elements in our natural world are metallic. And if you've learned anything in chemistry, you'll know that they all exist pretty much on the left-hand side of the periodic table. In the start of Year 11, we learned about the trends within the periodic table, and we learned about a thing called electronegativity, which is the ability of an atom to gain electrons. And if you remember, all the metals have a low electronegativity, meaning that they don't have a great ability to hold onto the electrons, and if they want to react, they'll actually lose electrons. So if we have a whole bunch of metals together, combined and pressed as a pure just metal, all these things will want to lose their electrons. That allows us to come up with an idea of what they would look like, and this is it here. We end up with a thing called the metallic bonding model. This shows metallic cations in a lattice, so a structured lattice of positive metal cations, swimming in a sea of delocalized electrons. These electrons, these little negative particles, they have been lost from our atom because our metals have that low electronegativity. They don't want to hold on to the electrons, so when they get together, they're all just swimming around, and those electrons have no real affinity to any of these atoms. There is a force holding it together, otherwise our metal would just melt in our hands, but that force is relatively weak, and it's an electrostatic force between the positive cation and the delocalized electron. Electrostatic means a force between positive and negative. So therefore there's a force holding these metals together, and that's the electrostatic force between our positive cation and our negative delocalized electron. The model we have above can be used to explain a whole bunch of properties that we see in metals in our everyday life. As you know, metals are malleable, which means they can be bent into different shapes. The reason this model fits is because that these cations can be pushed with a force, but they can still be held together by delocalized electrons. Metals are conductive, which means they conduct electricity. Electricity is the flow of electrons, and because our metallic bond up here says the fact that we have delocalized electrons, that these electrons are not held down tightly, means that these metals can conduct electricity. Electrons are free to move, they're charged, so therefore they can conduct electricity. Our last two properties are a bit strange, and you're just going to have to take my word on these ones. But first one is the fact that metals are shiny. Electrons have the ability to reflect light, and the fact that we have delocalized electrons in our metallic bond means that they can be reflecting light and shiny. Lastly, they have a weird range of melting points, and that's dependent on the force of that electrostatic force.